So we know how to find the derivative of a polynomial. We know how to find derivatives of sine and cosine, and even tangent and all of the other trig functions. But what about exponentials and logarithms? Well, let's start with, let's say we have e to something. And so this is going to be a rule that can be used for anything. E to some kind of function of x. Then the derivative is going to be e to whatever that exponent was times the derivative of the exponent. Yep, it's beautiful. So if we had e to the sine x, it's going to be amazing. You're going to say e to the sine x, and then the derivative of the exponent. So times cosine x. E to the 2x plus 3 is going to be f prime of x equals e to the 2x plus 3 times the derivative of that exponent, which is going to be times 2. So I'm just going to put the 2 in the front. What about here? Oh no, there's a number in front. No problem. 3 e to the 2x times the derivative of the exponent. So that's really 6 e to the 2x. Oh, it's product rule. Product rule. First function, second function. So, product rule. The derivative of the first is 2 times the second. So times e to the 3x plus the first function, just like it is, times the derivative of the second. So times e to the 3x, derivative of the exponent, so times 3. I mean, I can make that a little prettier if I wanted to, but we get the idea. So here, product rule, f prime of x equals derivative of the first times the second function plus the first function, just like it is, times the derivative of e to the 2x, which is going to be e to the 2x times 2. Oh, chain rule. Well, before we start, let's rewrite it. Square root is really to the 1/2 power. Wait, power to a power? I think I can multiply that together. So if I multiply those two exponents, I'm going to get e to the half of 2x is x, and half of -6 is -3. That's pretty. Sometimes you don't have to use the chain rule if you can simplify it first. So, e to the x minus 3 times the derivative of the exponent, which is just a 1. That one's nice. That turned out kind of neat. What about, quotient rule? So let's remember our quotient rule. Derivative of the numerator is going to be e to the 5x times 5. So I'm just going to put that as 5 e to the 5x times the denominator minus e to the 5x times the derivative of the denominator all over the denominator squared. I think I can't resist. I've got to simplify this a little bit. That's going to be 15x squared e to the 5x minus 6x e to the 5x over 9x to the 4th. I could even simplify it further. What if I factored out what these two have in common? Well, they both have a 3x, and they both have an e to the 5x. It's going to leave me with 5x minus, when I factor out 3x from there, it's just going to be a 2. And I think I'm going to rewrite 9x to the 4th as 3x times 3x cubed. Why would I do that, you ask? Well, the 3x's can divide out. Turned out pretty nifty. Okay, so the next one is natural log. If f of x equals the natural log of g of x, so some kind of function of x inside, then the derivative is going to be 1 over g of x times the derivative of g of x. Actually, I could write that a little prettier, huh? Since I'm multiplying by that, that would just be the derivative of g of x over g of x. Let's try it. So 2x minus 3 is the inner function. So it's f prime of x equals 2x minus 3 in the denominator. The derivative of that goes in the numerator. Oh, beautiful. Next one. 3x squared plus 2x goes in the denominator. And the derivative of that is going to be 6x plus 2. Cosine's going to go in the denominator. Derivative of cosine is negative sine. Oh, that's tangent. Cool. Oh, I need to rewrite this one. Hold on. Okay. So that's the natural log of 2x minus 4 to the 1/2 power. So when I take the derivative, that's going to be in the denominator. And then I need to take the derivative of that in the numerator. So power down, 1/2, 2x minus 4 to the negative 1/2 times the derivative of the inside, which is 2. Ooh, 1/2 and 2. Now when we have a negative exponent, that could be moved to the denominator. So I only have 1 left in the numerator. 2x minus 4 to the 1/2 and another 2x minus 4 to the 1/2. So this is like the square root times the square root. Ooh, that's just going to be 1 over 2x minus 4. The next part of this lesson is finding values of derivatives using the calculator. So make sure you grab a calculator. If we need to pause it, go get a calculator. So, to find the derivative in a calculator, we're going to press the alpha button and then the window button. So it's alpha F2. And the third option is a beautiful option. It says derivative. Now, the d dx, we want to go with respect to x. So this is going to have an x there. Inside here is going to be our function. So 3e is on ln to the x sine x. And I need to close the parentheses on that sine function. And we're evaluating this at -2. So over here is going to go -2. And it gives me the answer. So f prime of -2 is going to be -0.538, 3 decimal places. Is f of x increasing or decreasing, or does it have a horizontal or vertical tangent at that point? Well, since f prime of -2 is less than 0, then f of x is decreasing at x equals -2. What about the same function at 1? So I don't want to retype the whole thing, so what I'm going to do is go up, select it, and then just edit down here and put 1 instead of the -2. And I get 11.268. So what does this mean about f of x at 1? Well, since f prime of 1 is positive, then f of x is increasing at x equals 1. Hard part on these is just going to be typing in the function in the calculator. So alpha, window, derivative, and it's always going to be x there. I need a fraction. Now if you didn't know this trick too, if I press alpha and then my y equals button, I get an option to have a fraction. Then I can type in ln cosine x, need to close parentheses twice there, over x squared. And we are evaluating this one at pi over 3. So pi divided by 3. I get -0.372. So f prime of pi over 3 is -0.372. So what does this mean? Since f prime of pi over 3 is less than 0, then f of x is decreasing at pi over 3. At x equals pi over 3. Be very specific. So what about the same function but at pi? Okay, so I just want to change the x value. So I'm going to go over here and I'm just going to delete the division sign and the 3. Oh, it said it's a non-real answer. What does that mean? Well, that means it's undefined. So I didn't get a negative number. I didn't get a positive number. I didn't get 0. So since f prime at pi is undefined, I'm not increasing, I'm not decreasing. F of x has a vertical tangent at x equals pi. Ooh, all right. Wait. So alpha window 3, this is always an x, e to the, and now I need to have tangent 0.34x, close parentheses, and we're evaluating this when x is 0. I get 0.340. So since f prime of 0 is greater than 0, then f of x is increasing at x equals 0. Alpha window derivative. Whoops. 5. Ooh, how do I do sine squared? Well, I need to put, let's talk about that. So I need to do 5 parentheses sine of ln of x, close parentheses there, close parentheses there, squared. So parentheses sine ln x, 1, 2, 3. So 1, 2, 3 squared. And we're evaluating this when x is 1. So I'm putting a 1 there at the end. Oh, -5 times 10 to the -6? What is that really? If I've got that many zeros, that's basically a 0, right? So since f prime of 1 is basically 0, then f of x has a horizontal tangent at x equals 1. The beauty about now knowing how to find the derivative in the calculator is it's going to help us with word problems. So when the value of the derivative is positive, we say the function is increasing. When it was negative, we say it's decreasing. When speaking of quantities increasing or decreasing, they do so at a certain rate. We already understand the derivative is the slope of the tangent line. Remember, slope is your rate of change. The derivative of the function actually represents the rate at which a function is changing. So let's look at what we can do. So for this problem, I have a function, and I'm going to be answering several questions about it. So one thing you can do is go to your y equals, and let's put that function in there. 560 e to the sine x. So now that's in y1. That's handy. I don't want to have to keep retyping it over and over and over. If I wanted to find the value of f at 1/2, what you can do in your calculator is do y1 of 1/2. Your calculator calls things y1, y2, y3 instead of f and g and all that. So there's a shortcut on these 84s to get y1. If I press alpha trace, the very first option is y1. and I can just do y1 of 1/2, and I get 904.482, because that would round up to a 2. 904.482. What does that mean? So let's look at the problem again. The number of people entering a concert can be modeled by this function, where t represents the number of hours after the gates are open. So 1/2 would be half hour after the gates opened, (904) people have entered the concert. The next one is f prime of 1/2. So let's look how we can do that in here. We're going to do alpha window derivative. And since I saved my function in y1, I can do alpha F4, which is the trace button, and just put y1 in there and evaluate it at 1/2. I get 793.757. Let's think about what this means. Well, the time is still half an hour, so half an hour after the gates open. This is the rate of change. So people are entering, because it's positive, the concert at a rate of 793 people per hour. This is our rate of change at that moment. How many people have entered the concert 2 hours after the gates have opened? So which one would I go to find out how many people entered? Well, that's going to be f of 2. So I'm going to go y1 of 2, and I get 1390.244. So this means 2 hours after the gates opened, (1,390) people have entered the concert. Is the number of people entering increasing or decreasing at that time? So we're talking about that increasing or decreasing. We want to look at the rate at that time. So I need to do, I could just go up and select this and delete it to say 2. Negative 578.545. What does this mean? Well, since f prime of 2 is less than 0, then 2 hours after the gates have opened, what is true? Well, the number of people entering the concert is decreasing at a rate of 578 people per hour. Last example. After being poured into a cup, coffee cools so that its temperature is represented by this function. T is measured in minutes, and T of T is measured in degrees Fahrenheit. So the first thing I would do is plug that baby into the calculator. Plus 110 e to the, see, that's negative, and I'll have to use x in my calculator, but that's okay. X divided by 2. Now I'm going to quit and go back to the screen. What is the temperature of the coffee 5 minutes after it's been poured? So that's T of 5. So alpha F4, which is the trace button, gives me my Y1 of 5, 79.029. So what does this mean? It means 5 minutes after the coffee is poured, the temperature is 79.029 degrees Fahrenheit. Is the temperature decreasing faster 1 minute or 3 minutes after it is poured? We know it's going to be decreasing because coffee is cooling, but when is it cooling faster? Well, we'll need to find the derivative at 1 and find the derivative at 3. Now this one wouldn't be too bad to do by hand, but most of these problems will be calculator based. So I'm going to select Y1, and the first time around I'm going to plug in 1. Negative 33.359. 33.359, and what this really means is that's degrees Fahrenheit per minute. So I can go back in, arrow up, select that response, and change it to a 3. Negative 12.272. That's also degrees Fahrenheit per minute. So when is it the temperature decreasing faster? The temperature is decreasing faster one minute after the coffee is poured. And why is that true? Well, because if we look at the absolute value of that derivative, that's 33. That's bigger than the absolute value of the derivative at 3. Now there's some problems next. Practicing with the derivatives of E and of ln, which would be very helpful to practice.